Alright, so today we're talking about numerical solvers for differential equations. Okay, and so we'll assume that we're given the differential equation, first order, y prime equals f of ty, with y of 0 equals t0. Okay, so that information has to be given. And so what we want, or output maybe I'll say, what we want the algorithm to do is to provide a numerical estimate of y of t. And so how is it going to do that? Usually this is provided as a vector of values of y evaluated at some specified set of time values. Okay, and so by that I mean, geometrically, right? If this is your t0, I have to be told what my t final is. Okay, so that needs to be provided. And usually what's also provided is that the time values will all be evenly spaced. Typically, the time values, t's, are evenly spaced, although they don't necessarily need to be, but we'll see that later, I think. There's some ways of adapting the step size so that when the function's nice, you can use large step sizes, and when the function is getting bad somehow, we'll try to squeeze together the step size. But that's later. I don't want to get into that right now. So typically t's are evenly spaced. And so the space in between, the delta t, is denoted, or is the step size. You'll see it referred to step size. And we're going to use the notation h. That's kind of classic. Okay, and so what you're being provided then is a numerical approximation, right? This is like y1, this would be like y2, this would be, this height right here would be y4, or y3, this height would be y4, this height would be y5, and so on. Okay, so hopefully the underlying solution, right, looks nice. Okay, good. Okay, so how are we going to get this is the question. And so mainly the way to think about this is just, instead of going all the way from t0 to t final, we just want to think about how do we get, I'm getting updates here, how do we get from tn, some given time, to the next step over tn plus 1. So I'm going to assume that I've got my yn here, right? So I know that I'm at this point. And so the question is if I go across by h units, which is our delta t, how far up or down should I go, right? And so, of course, we remember we're given that y prime is equal to f of ty. Okay? So the kind of the classic first step approximation is to assume that your function is linear here. Okay, and so if we assume that it's linear, and what is the slope at that point? I'm going to get rid of this. the slope here is given by f of tn comma yn, right? So that is a known function, a known value, right? Once I know what my tn is and my yn, then I plug those into my f to get the slope. And so then what is yn plus 1 going to be? Well, if I move forward by h units, then that means I go up or down h times the slope, right? That's how a line works. And so what we get here from that formula then is that yn plus 1 is equal to yn plus h, maybe I'll make my h more of a script, h to distinguish it from n, times f of tn yn. Good. So this is Euler's formula, or Euler, not formula, but method. Euler's method. And actually, you know, for being such a intuitively clear method, I think it actually works fairly well. So maybe we can think about what our how we would implement this in MATLAB or Octave. Implementation. In MATLAB/Octave. So in this case, I'm going to write a function, and so we'll see how to use this function. So in MATLAB or Octave, the very first line of your function needs to say function, and then we'll use square brackets for our output, and our algorithm output will be a vector t and a vector y, and then we'll call this Euler underscore forward. By the way, no white space in the name, please. And then the input to Euler forward are going to be these things, right? I need to know the function f, I need to know the step size somehow, and I need to know what the time values are. So I'm going to have my f there, my initial time, t, I'll say t init, although it's giving some space there, y init, t final, and then let's say I'm going to pass in the step size h, because a lot of the homework we pass that in as the step size. Okay, and so what will the let's see. Okay, I think I can just go ahead and continue. Normally I'd talk about some of the comments, but I'll let you think about what kind of comments you would write. By the way, if in MATLAB or Octave, a percentage sign is used to denote a comment. Okay, and so what I'm going to do is first, because I know my initial and final time and step size is, I'm just going to go ahead and define the entire vector time, t, and so that'll be t init, and then use the colon h colon t final. And so this is going to build my time values automatically for me. And so the number of steps that I'm going to take, I'm going to call n, and that was going to be the length of t. Okay. And now just for good practice, I should say y equals zeros, and then we'll say it's 1 comma n. So I'm just reserving storage space for the vector y that's going to be output. Now I initialize whatever I need to initialize. Y of 1 is y init, right? And that's it. Let's get our algorithm now for I equals 1 to n minus 1, then y of n plus 1 is equal to y of n plus, oops, sorry about that. I'm using I as my index. I plus 1 is equal to y of I plus h times f of t of I, y of I. Okay, semicolon, end. And now we're done. Okay, so the problem here is, by the way, so you would type this in and save this file as the file Euler forward.m. Okay, because when we're going to use it, we're going to do a sample use in the next video. We're going to call, in order to use this function, we'll call Euler forward.m. Okay, so that needs to be the file name. Good. So in the next video, we'll talk about how to actually call this using MATLAB. All right.